Hey folks, Sonic Fan here, and we are back looking at remote controlled AC switching outlet adapters. These are super cool. I'm a huge fan of them, and since my last video on this is one of my most popular videos with a whole 10 views in the past month or so, I felt obligated to make yet another one. Just kidding, I don't think anybody cares about these, but I do, and I like documenting cool repairs and things, so I'm making another video about these. Anyway, this is a wall outlet that I bought for about 10, 12 bucks, maybe more, maybe it's 15, I don't know, a few years ago. And it's actually supposed to be weatherproof, which is cool. I don't really plan on putting this outside, but nice to have the option, I guess. But it broke, and instead of just going and throwing this in the e-waste and buying a new one, which I could very easily do, I rather learn about it, learn why it broke, and also because I like it. I don't want to get another one that might have a remote control with different keys, like the clicky keys, tactile push buttons, instead of the nice soft rubberized keys that this one has, which I really like. And also, yeah, it's really nice to learn about things. Like I said in the other part of this video, I really like opening up budget electronics because they really show how you can design something at a low cost threshold, and that's pretty nice. Go ahead and cover the lens so it'll refocus here a little better. It's giving me focus issues. Anyway, the design for this thing is pretty cool, and it's really common for these types of sort of, I guess you might call it an appliance adapter or electrical adapter, and it's pretty cool. So I'm going to go into the details. I'm going to put some of the stuff under the microscope, and even though it's, you know, pretty straightforward, but mostly I want to explain how the circuit works, and let's see if I can actually, I don't know if I can fit the whole circuit under the microscope very well. Yeah, it's not going to look that helpful. Let's just put it up to the camera here, or get the camera zoomed in maybe, and explain it like so. Get some better lighting, perhaps. And the other thing too is I can actually make this a little more robust, a little safer than it was stock by doing this repair and, you know, possible couple upgrades. Also, be very careful when you're working with AC mains. I said in my other video, just don't work with AC mains because I don't want somebody to get hurt. So unless you're like using a lot of proper safety precautions, you have a fire extinguisher, insulation material, all that kind of stuff, be very careful with working with AC mains. Anyway, so this is AC mains is 120 volts here, 110 to 120, and the way this works is pretty cool. You have your ground wires are green, of course, and that just goes to the plugs directly, and then you have your hot and your neutral. The neutral gets passed just through the relay. When the relay has 12 volts, it'll bloop, flip the neutral to the output. The way this works, though, with the hot one is it goes through a, there were two inductors here that essentially worked like a transformer. I'm not sure exactly how that works. I guess it's four pins makes up a transformer. Kind of a trippy way to do it, though. Very cool, very budget. That transformer then went to a bridge rectifier. By the way, you can get away with this because it's such a low power device. So these two inductors formed a transformer, went to a bridge rectifier, which made about 15 volts. You have a DC capacitor to smooth it out. And then also before it reached the transformer, you also had an RC network here to kind of smooth things out. There was a resistor, and then there was this blue capacitor here, which I had to look it up, but it is a metallicized polyester film capacitor rated at 160 volts, and that created that's your AC stage. So after it goes to the bridge rectifier, it becomes 15 volts, very low power. You need the big capacitor to smooth things out because it's going to be a very dirty 15 volts with a janky, simple but janky transformer like that. And then once it's 15 volts, you can now feed the relay safely, that 12 volts, but you have to switch it, right? You have to have some switching circuitry to do that, to tell it to turn on. So to do that, you have to power a microcontroller. To power the microcontroller, what do you need? You need 5 volts usually, or 3.3. In this case, it's going to be 5 volts. You need a lower voltage. And so this chip right here, this is a 78L05, which is in a TO92 package. This is a 5 volt step-down regulator. It burns off the excess voltage, makes 5 volts. And then that goes to your microcontroller and your receiver chip, which is collecting the NRF radio through an antenna. So this little antenna. The NRF is, of course, transmitted from the remote, and that interprets the signal from the wireless signal, probably a 2.4 gigahertz signal, and it's tuned with this trim inductor. There's only 3 pins here. There's a voltage in, ground, and output. That output then goes to this microcontroller. This microcontroller has had its part number sanded off, as you can see. So we don't know what it is, but it's probably just some very basic general purpose microcontroller. That microcontroller, once it gets the signal, it does 2 things. One is it switches on an output to turn on this LED, this red LED, which goes to these resistors here. This one resistor here specifically. And the other thing it does is it switches on this NPN transistor, which is, I looked it up, it's a C1815, 2SC1815. It's a general purpose NPN transistor. And then in turn, that general purpose NPN transistor basically says, okay, 12 volts you can now pass to the relay, and then the relay switches on the AC outlet. So that's how things usually work. When you have a high load or a high voltage, you need to switch with a big bulky item like this, like a relay. You have to have usually a smaller switch to handle the logic coming from a microcontroller. Very, very common, pretty unavoidable technique. That's just good to know about. Lastly, there was a diode here. It's now on the underside of the motherboard, but there's a diode that was here, which is very important, and that's the feedback diode for the relay, because the relay is an electromagnet, and electromagnets store voltage, and so if you turn off the relay without that diode, that voltage has nowhere to go, and it can actually blow out your relay or your output. Most probably the relay, because the output's just a switch. So yeah, it would blow out your relay if you didn't have that diode, which may be what broke this when I was messing with it before. Although it broke originally because of the AC, the janky kind of AC. I'm pretty sure what originally broke was the bridge rectifier, like the cheapo diode bridge rectifier combination here, or possibly one of those 2 janky inductors. But one thing I wanted to show that's a little interesting is the pinout of these relays. It's actually somewhat standardized, surprisingly, because I found another one in my parts bin. And so I'm just going to go up here to the screen and show you all. This is the bottom side of the relay that I took out, and the one that's in there is very similar pinout. And how this works is, how a relay works, first of all, is you give it positive DC voltage, usually 12 volts. And then there's an electromagnet, and through the amazingness of electromagnetic induction, it will magnetize a switch inside here and push up the switch through magnetism, through the electromagnetic inductor, to connect 2 points. And so in the case of this guy, the 2 points are here and here. So these points are not connected, but when you give it 12 volts, the switch connects. And again, this is what's cool about relays, is they're electromagnet switches. They work with magnetism. So this switch is in no way electrically connected to the 12 volts that you're giving it. It's a magnet. The 12 volts just creates the magnetic effect. And so that way it's what's called electrically isolated, which means these 2 pins can be anything you want, and you don't have to worry about ground shortages or anything else. So in the case of our circuit, of course, these 2 pins are the wall voltage, the hot wire coming from the AC outlet, and these two are created in our 12 volt janky power supply. And of course, if you look at the top of a relay, it'll tell you what it's capable of, usually some pretty high current ratings, extremely high in this case, and usually higher current for VAC or AC outlet voltage AC, because it's switching, than it will be for a DC current. And then also, I think these are going to be the absolute max thresholds on the right here. And then this, of course, is the frequency coming from the wall. 60 hertz frequency is standard for North America. And I guess this part number is pretty common, pretty cheap. Some suppliers, I think, sell this really cheap. I mean, this whole thing was very inexpensive, so wouldn't be a shock if that relay was of not the best quality. So yeah, folks, that's basically it. I'll show the underside just to give an idea of what the layout kind of looks like a little bit too on camera here, since I have a good setup here. And this is the diode. This is the flyback diode I mentioned, which goes across the two. These are the 2 points of the relay, here and here, the positive voltage and ground. And the trace actually broke here when I was trying to push the diode through, so I had to run a wire there. Not uncommon on these cheap PCBs that traces will just break if you're not super gentle with them. These are very, very cheaply manufactured. And the two AC things that are switching are here and here. The two pins I showed before, the isolated output is this pin and this pin. So the relay makes up AC and DC. Down here, these 3 pins are the 5 volt regulator, which goes to these 3 pins, which is the NRF decoder, and then of course the microcontroller, which is over here. And then, as I mentioned, the neutral line just goes straight to the output, as does the ground. You're only switching the hot line. So yeah, hopefully that's interesting and helpful for folks. I think these things are super cool to learn about. I love learning about inexpensive electronics and how they're designed for budget, because then you can design things for budget and kind of learn from the design work that other people have done. A lot of times these are designed in China and overseas, so there's a lot of brilliant engineers over there, folks. Always makes me sad when I hear people that are against saying anti-China things, because China does a lot of great stuff, you know. The governments of all countries tend to have problems sometimes, but the people there's a lot of wonderful Chinese people that are brilliant engineers and bring us cool things like this. That's all for this video. If you want to see and you're interested in these kind of things, please let me know, because I know most people are interested in stuff like this that I design. But I also like doing repairs for budget items as well, and I think there's a lot to learn there. I forgot to mention in the last video how I was going to be repairing this. Dope. I was giving a rundown of all the features and everything. The way to repair this is actually very easy, relatively speaking, because it doesn't require like a lot of parts or anything. The AC circuit's blown. The bridge rectifier was blown. I took all those parts out. So what do I do? What do I need? Well, I need 12 volts, right? I need 12 volts to drive the relay and convert to 5 volts for the microcontroller. I don't have that now because all that AC conversion stuff is gone. All I have is the AC outlet pass through. So if I just need 12 volts, all you need is a 12 volt adapter like this. And you can just cut these wires and feed those to the output, the capacitor, and then you can actually solder to these, the AC plug here. It's kind of funny and janky, but you just solder 2 wires to there, preferably with a fuse for both the output and input. And you know, you can solder those 2 wires to the neutral and the hot. That'll turn this power supply on when you plug it in, and then 12 volts will go to the capacitor, the large capacitor there, for your what was previously the 15 volts. And then you'll be good to go, because then you'll have that 12 volts and everything will get converted for the microcontroller. And now you'll have a legitimate 12 volt nice power supply powering this circuit instead of the janky kind of, you know, but useful one that was in here before. And of course, the one in here before was very, very small. And that was the advantage, whereas this one's larger. So what I'm going to end up doing is just, it's going to look janky, but it'll work great. I'm just going to glue this or tape this on the top like that. It'll look kind of funny, but it will be a fully functioning, totally recyclable. And this is a power supply was never going to use. So yeah, just reusing old parts around the house, making cool things, repairing cool things. It's fun to do, kids. All right, folks, here it is. All done. All repaired. And yeah, nothing going to blow your mind or anything, but I just got the AC wires wired up to the AC of the 12-volt adapter, and the 12-volt wires going back in to power the circuit. And if I can find the remote, oh, here it is. The remote, by the way, I've modified with a lithium-ion battery, so I can just unplug this and recharge it whenever I want, which is much nicer than the coin cell ones. And I'll go ahead and plug in a USB adapter with LED light that turns orangish red when it's charging, so you can see that the AC outlet's working. And let's give it a shot. Ta-da! Turns on. You can hear the nice click of the relay. Turns off. So yeah, that's pretty much it. Nice little remote AC outlet repaired. Even if it looks a little janky, it's nice and durable and going to last a long time, hopefully. What did I end up doing? Removed the AC. Just an overview of what I eventually did. Removed the AC circuitry that had blown with the blown bridge rectifier. I replaced the flyback diode, which probably wasn't broken, but just in case. And I replaced the relay, which may have broken from the flyback diode. So there's a new relay, new flyback diode, and then of course replaced the AC circuitry with a proper 12-volt wall adapter. And wired the 12 volts back in. And that's it. So yeah, fun little project. Have fun hacking and repairing and all that good stuff. This is Sega Sonic Fan, signing out.